Alright y'all, welcome to the Solutions Take-Home Test video key. If you haven't watched one in a while, any question you see if you're working ahead that's highlighted in blue is one I'm going to work through on this video and explain. Anything that's highlighted in pink on this take-home test means I am not going to do it on the video. You're expected to do it on your own. My explanations on the we do problems might help with how to do those other ones. Okay, vocabulary is a huge part of what we're doing this unit. So take a look at this stuff. It's a big deal. Questions 1 through 13. So this is what I've got for y'all. Okay. I wanted to talk about number 2 for sure. Temperature and the solubility of solids in a liquid have a blank relationship. Okay. Solubility is dissolvability. So temperature and how dissolvable solid is blank relationship. So I would say at higher temperatures, solids are more soluble. They dissolve better. Like sugar dissolves better in hot tea, or cocoa powder dissolves better in hot milk. So if both arrows go up together, that is a direct relationship. Okay, so we can cross out direct. Alright, number 4 is on your own. Number 5. To blank a solution means to decrease its concentration by adding more solvent. So the universal solvent is water. So if we're decreasing the concentration by adding more water, we're diluting it. Okay? If you add more water to your Kool-Aid so that more people can have Kool-Aid, you watered it down, you diluted it. It won't taste as good. D-I-L-U-T-E. Alright, dilute's gone. Number 7, a blank solution is when more solutes could still be dissolved. So that means this solution is not done dissolving, it's unfull or unsaturated. Okay, an unsaturated solution can still dissolve more solutes. Okay, push pause if you need to check on that. Otherwise, let's move to the bottom half of this page. Okay, Kool-Aid completely dissolved in water creates what kind of solution? So the key word here is solution. All solutions we learned are homogeneous. Okay, so I know it's not going to be hetero. Okay, Kool-Aid looks the same. You can't tell where the sugar or where the water is. And then kind of the difference here is compounds. Compounds are chemical compounds. They're pure substances. There's no such thing as a homogeneous compound or a heterogeneous compound. Those are my two kinds of mixtures. So that helps me know it's a homogeneous mixture. Be careful that you don't get excited and just pick the first answer choice that has homogeneous. We've got to take out the garbage and eliminate wrong answers. Okay, let's take a look at the rest of the bottom half. Number 16. Water is the universal solvent. That's something to memorize. It's up here as well, because it is a very blank molecule. Water, H2O, is 2 nonmetals, so it's not ionic, it's not insoluble, it's not relevant, it's polar. Okay, and that was something to memorize. We talked about this in class, that water is a polar covalent bond, which means it doesn't share equally, negative half, positive half. That's why water is so great at dissolving things, because of its polarity. Number 17. A ring that is made out of an alloy of 18 karat gold. Okay? That is made of 75% gold and 25% copper. The solute is blank, the solvent is blank. So my favorite way to remember this, and I taught my students this, is you count the letters. Solute is 1, 2, 3, 4, 5, 6 letters. Solvent is 1, 2, 3, 4, 5, 6, 7 letters long. Okay? So always my bigger word is going to be my bigger ingredient. So in this case, it's mostly gold. I would say gold is a solvent. My smaller word is my smaller ingredient, or ingredients. So copper. It's a good trick, right? Take a look at the other ones. I included some hints on the ones that I already done for you. And then let's start looking at page 2. Okay. For page 2, we're looking at those solubility curves. And I really stress to my students that you might want to use colors. We'll have highlighters and colored pencils available for you on test day if you want to bring your own. You may. but I want to show you the stuff first. So, which substance is the least soluble at 70 degrees Celsius? So degrees Celsius is on this axis, it's the x-axis, and solubility is on the y-axis. So if I were to say which one's the least temperature, you would know that means towards 0 on the x-axis. If I'm saying least soluble, that means closer down towards the 0 on the y-axis. So at 0 degrees, okay, right here, the lowest one is this one. And be careful, I'm just going to use some color and say the green line is KNO3. So that's going to be my answer. Potassium nitrate, KNO3. Alright, take a look at how I answered number 22 for you. Number 23, if we dissolve 80 grams of KNO3 in 100 grams of water at 50 degrees, the solution is considered. So we still want a box and circle here. 80 grams, 100 grams, 50 degrees. Now one thing to be careful about is my unit up here. The 100 grams of water that's in this question right here just means according to this graph. So I actually want to cross that out. Doesn't matter. 100 grams of water just means in this instance, I guess. So KNO3 I'm going to highlight down here in green because I've already decided to make this my green line, so my brain can just focus on that information and I can ignore the other lines. Alright? So 80 grams is up here. I'm going to say this Y value at 50 degrees. So this X value. And if I plot that point, it falls exactly on KNO3's solubility curve, which means it's saturated. Let's say it's exactly on the line, means saturated. So if it's under the line, okay, if that point was down here, I would say it was unsaturated. If it's supersaturated, it's above the line. So if I plotted a point and it was up here, above the curve, and then insoluble, I just said you dissolved it, so that's garbage. We get rid of that. Okay. Number 25, we dissolve 110 grams of NaNO3 in 100 grams of water, which I can cross that out. That just means according to this table at 40 degrees Celsius. So I haven't looked at NaNO3 yet. So I'm going to go ahead and just pick orange for that one. So I know to focus on this information and say this is my NaNO3. Okay. So if I dissolve 110 grams up here at 40 degrees Celsius, and you look, that point is right under the line. It's pretty close to the line, but it's definitely under it. So on the line is saturated, which this isn't. Under the line is unsaturated. I still wanted to take out the rest of my garbage. Above the line would be supersaturated, insoluble is garbage, so okay, I can say B confidently, that's my answer. And then just realized I skipped 24, so we'll go back to it. 24 is about KNO3 again, which I've already decided was green, and NaCl, which I'm going to make purple. Okay, so my NaCl is right here, and that's right above this line. So I'm being asked at what temperature does the green and purple line have the same solubility, which means where do they intersect each other? And that's right here. That's where green and purple meet. So that would be at about 39 grams, but they're asking me for temperature. So I'm going to read down here. It's not quite 25. I'd say probably about 23 degrees Celsius. Really, any answer between 21 and 26 is going to be acceptable. It's not a very precise graph, so we won't be very precise in what we expect from you. Okay, but that's how you know if it's the same solubility. And number 26 is a really important one to know. Okay, I want you to finish answering this question. But it said, are there any gases in this graph? Why or why not? So we talked about this back on page 1. I said as temperature increases, the solubility of solids increases if it's solid. That's a direct relationship. So all of these are solids because all of them have a positive slope. For gases, as it gets hotter, the gas is less soluble, it's less dissolved. Okay, and we'll talk more about that in a little bit, but that means it's an inverse relationship. So a gas would look like this on this graph, and there's nothing with a negative slope, so that's what I said for my answer. Okay. Take a look at the bottom half of this page. I've got an extra credit code for you here. Go ahead and add in this +2 if you write, say it like a nerd. Say it like a nerd. Okay? You need to use full sentences and vocabulary. Okay, so talking about why it crystallizes, or you don't want to just say it goes flat. That's not enough. Okay. So for number 29, I didn't answer it for you, but I did give you your nerd words. You should be using words like polar, insoluble, and nonpolar in order to answer that. And if you need to, go back and check your notes. Vocabulary is such a big part of this test. It's not math-based. It's very much, do you understand the vocabulary? So make sure you're practicing. Okay. Oopsie, and I'm showing all of my answers here. This is the top of page 3. So, particle diagrams. Okay, I gave you some hints on how I answered these two, but for number 30 together, the particle diagram represents which of the following? Okay, so I don't see anything stuck together like I do. I see these things stuck together here, which would represent chemical bonds. So this is not a chemical compound. I can say there's no compounds here. There are definitely elements there. Okay, so that looks okay. There are definitely elements, but it's not the same kind of element over and over again. So it's not a single pure element. This is going to be a mixture of two different elements. Okay. Getting into these ones, for problems 33 to 42, you have to show your work to get credits here on the take-home test and on your in-class exam. And then when you do math and chemistry, you guess. Okay, your teachers all have this poster in our classrooms. That means you identify the given, the unknown, pick your equation, then substitute solve. Okay? And so for extra credit, I'm going to have you do just that. Okay? If you write +2 here, then you write your givens. Right? We box in our givens, and we circle our unknowns. Alright, that's going to help anytime you're doing math, not just in chemistry. Alright, so down here I gave you the answers for 33 and 34, so you can check what you got. You still have to show your work if you want credits. Okay, number 35 and 36 we're going to do together. And what you'll notice is I went through and I did this. I boxed in my givens in green, and I circled my unknowns in red. So I went through and I did that as well. And then I labeled them. Is it M for molarity, L for volume, or mole for moles? Alright, I'm going to switch to pencil because I will make a mistake otherwise. Oh, let me see if I can find one. Okay, so this question is asking me to find the volume in liters. So there's the unit in my answer. Volume in liters needed to make a 0.1 molar solution if you have 0.25 moles. So I know on my periodic table where it says solutions that I'm using this equation because I've got volume, moles, and molarity or concentration. Okay, so the equation I'm going to pick is molarity equals moles over liters. Okay, I can plug them in where I know what my M is. 0.100 equals moles over here, 0.250 over liters, which I don't know. That's my X. Okay. So I taught my students we can do the same kind of math we did with Crazy 8 in our gas laws unit. So for Charles or for Gay-Lussac, we can do the same thing if we do this. And we say that that's over 1. Because putting molarity over 1, dividing anything by 1 doesn't change it. But now I've got a fraction equals a fraction. So it's more clear that I'm supposed to cross multiply and divide. So if you know that crazy 8 shortcut, I want to make the 8 so x isn't in it. That means this, like that. That's my crazy 8. So this times this divided by this equals that one. Okay, that's how the algebra works for that. So I'm going to say 1 times 0.250 divided by this one, 0.100, equals that one. Okay, 2.5 liters. And I'm even going to write 2.50 because of significant figures, which you don't have to worry about, just explaining. Right. Number 36 is a meaner problem, and that's all right. It says calculate the concentration, which I'm supposed to know means molarity, that's the same thing, of 400 grams of copper sulfates, okay, copper 1 sulfates, in 4 liters of solution. So it's still this equation, but I don't have moles, which means we have to go grams to moles first. Okay, so we need to do some dimensional analysis. So I can say, for this one, okay, I'm going to write in 400 grams of CuSO4 as my given. This go down, grams of CuSO4, and I'm going to turn it into mole. Okay, and I know that 1 mole always equals the molar mass in grams. So 1 goes in front of mole on top, and the molar mass in grams of copper sulfates, copper 1 sulfate, goes on bottom, which I don't know yet. So we use the molar mass on the front of the periodic table. CuSO4 is 1 copper mass plus 1 sulfur mass plus 4 oxygen masses. So let's have fun with that one. 63.54, nope, I already did that wrong. 63.546 plus sulfur, okay, 32.066 plus 4 oxygens. So I'm going to use parentheses, okay. 4 times oxygen, 15.999, and close my parentheses. Get a molar mass of 159.608. That's not my answer, that's just the molar mass. 159.608. Okay. Woof. Now I need to convert this. So I multiply the top numbers and divide by the bottom. So I'm going to say 400 on top divided by 159.608 equals 2.506. Okay, equals 2.50 moles. Again, still not my answer. That's just moles. So now I have concentration is what I'm looking for. I turned grams into moles. That's going to go on top, and I have my volume that can go on bottom. So now I can substitute this in, and I can say molarity, X on top, equals moles, which I just found, is 2.50 over liters, which is 4.00. And I don't have to do any algebra here, at least because it's just my answer is the top number divided by the bottom number. So the top number, 2.5 divided by 4 equals 0.625. Okay. I think it ends up being like 0.627 if I didn't round this number, and that's all right. I'm going to say 0.62 and just leave that as good. And my units for concentration or molarity is just capital M for molar. So that's a more intense problem. We have to go grams to moles and then plug moles into our molarity equation. Number 37. I'm not going to finish number 37 for you. Okay. I'm going to go ahead and say for number 37, you're going to finish calculating it, but I will help you set it up, kind of like I did on 38. I set up the work, so you can see this. Okay. So for this one, again, molarity and volume I have, and I have grams. And grams doesn't fit anywhere in my equations here. None of my solutions equations have grams. So I know I need to turn grams into moles. Okay? So grams to moles, it's just one step dimensional. 5.95 grams of sodium nitrate, NaNO3. And I'm going to just go down my unit, grams of NaNO3. I'm going to turn that into 1 mole on top, because 1 mole equals the molar mass. So if I knock out that molar mass real quick, Na is 22.990 plus N, 14.007 plus 3 oxygens, 3 times 15.999. The molar mass is 84.994. Okay? And then I say my top answer divided by the bottom. So 5.95 divided by the bottom equals 0.070 moles. Okay, and look at that, it's really little compared to the overall molar mass. So now I have moles, molarity, and liters. I can plug that in. My molarity, X, equals moles, 0.070 over liters. Calculate and solve. Okay. Whew. Those are the more intense problems for sure. All right. Let's look at page 4. Okay. Similarly, on page 4, what I did was showing you this answer. Whoops, there we go. I showed you the answer, but I didn't show the work. So you can check your answer, but make sure you're showing work on this as well. Okay. And then I've got another extra credit code for you. It's our third one if you missed any of the others. What I'm going to do is I'm going to turn this a little bit, and I'm going to say if molarity is increasing, that means volume has to be decreasing. Okay, and that is an inverse relationship. Okay, so if you do your m's going up, volume's going down, that's inverse, and then put +2. So we know to give you some extra credit for that. Okay. Again, on this side, I boxed in my givens, I circled my unknowns, and the other thing I did is I circled this word of. Okay, I'm going to even highlight it on number 40. Okay, so it says what volume of this molarity, so 4 molar hydrochloric acid solution, would you need to prepare 300 milliliters of a 0.6 molar hydrochloric acid solution. So the word of is a magic word. It's an important word because it tells me that this volume and this molarity are stuck together. So these are either both 1s, M1V1, or they're both 2s, M2V2. It doesn't matter which one you pick as long as they're the same. So I'm going to say this is volume 1, this is molarity 1, and this one says of between them, so they go together. I'm going to make that volume 2 and molarity 2. And if you plug it in the wrong order, you will get the wrong answer every time. Okay, this is the equation we're using. M1V1 equals M2V2. And it looks almost identical to Boyle's law from the last unit. P1V1 equals P2V2. And you should remember that Boyle's was an inverse relationship. So if this one looks just like it, it's an inverse relationship. Okay? It's nice how that kind of comes back for us. So I know the equation I'm going to use is M1V1 equals M2V2. Givens, unknown, equation. Now I'm going to substitute. So my molarity 1 is 4.00, times volume 2, which I don't know. So I'm going to say X equals molarity 2 of 0.600 times volume 2 of 300. Okay. All right. Okay. So what I need to do is say combine like terms, or if it's X times 4, I need to divide it by 4 so that it cancels out. And then I'm going to do it to this side as well. So X equals this answer divided by 4. I'm going to say 0.6 times 300 divided by 4 is 45. And the unit I want is milliliters. So 45 milliliters. Okay. I didn't finish number 41 for you, but I did show you the work. Okay. And then I did box and circle on 42 for you, but you need to show your work and your answer for that one. All right, looking down at solubility factors, students, they struggle with this, and that's all right. That's why you'll see a lot of it's blue. We're going to talk through a lot of this, okay? Increasing the solubility of carbon dioxide gas, which is the carbonation in soda, means. So if I want an increased dissolvability of it, that means I want more gas in the soda, okay? So that's not meaning that the soda is going flat. Okay, I'm going to cross that out as garbage. The soda has more carbon dioxide in it. Yeah, that's increasing dissolvability, so B looks good. You have to decrease the pressure. If I open a can of soda and I decrease the pressure, that doesn't make it more carbonated, that makes it less carbonated. And they're insoluble, that's not true. So now I can say yes. Increasing the solubility means you have more dissolved. Okay. List 3 things you can do to make sugar cube dissolve faster in tea. Now sugar cube, S-O-L-I-D, is a solid. So 3 things we can do to increase the solubility of solids. Okay? You can crush the sugar cube up. Okay? That will help it dissolve better. You can stir it, but really the word we want for that is agitate. I-T-A-T-E. I'm like self-conscious that I spelled that wrong, so don't judge me. Agitate it or stir it, and then the best way to make solids dissolve better is by heating it up. Okay, number 46 now is talking about gases being dissolved, where 44 was about solids. Okay, as the temperature of water decreases, the amount of gas which can be dissolved blank. So I kind of put this little guy over here, and what it says is, as temperature of the water decreases, so I'm going to say water temperature is going down in this question, so the amount of gas which can be dissolved increases. That is something to memorize if you don't have it memorized. That temperature and solubility of gases are inversely related. Okay? So that means we prefer drinking cold soda because it's more refreshing. Cold soda will also stay carbonated longer. Hot soda will go flat more quickly. So if the temperature is going down, that means the amount of gas in it will be going up, inverse. Definitely not stays the same. Definitely not independent of temperature. Okay, so if you're going to get this wrong, at least pick B. Don't pick C or D. Number 47 says temperature and solubility have what kind of relationship? Bang, right there. We just talked about that one. Okay, it's inverse. Again, we haven't talked about logarithmic relationships yet. That's acids and bases. It's not exponential. So C and D are garbage. Direct is backwards, but at least it's not garbage. Number 48, temperature and the solubility of solids in liquids have what relationship? Okay, so same thing. I would say get rid of logarithmic and get rid of exponential. We don't want to pick those ones. Okay, and we're saying if temperature goes up, a liquid or a solid, which I guess is what I meant to say here, will dissolve better. So both arrows going up, that's our direct relationship. I'll make flashcards for this. This is something students get backwards all the time. Please, please, please memorize this relationship. Number 49. What are 2 things you can do to increase the solubility of oxygen gas in a liquid? Okay, so that's looking at this idea right here. What can I do to make it increase solubility? Well, I can decrease the temperature. So increase the blank, decrease the temperature. Okay, because colder soda will have an increased amount of carbonation or oxygen. And in order to increase how much oxygen is in there, I need to increase the pressure. Okay, and that's number 50. pressure, when pressure goes up, your soda can will get more carbonated. It's more soluble. When you open your can, okay, pressure goes down and your soda will go flat. The gas is less dissolved. And that is a direct relationship. Okay. Some students, this clicks, this makes sense to you. Great. If it hasn't yet, memorize. Please make flashcards. I know at least my students, if you make flashcards and bring them in, extra work is extra credit. So I will reward you for that. All right. We're getting close. Page 5. All right. Page 5, you'll see what I have at the top there for you. I have not only the answers, but how you should have known. And then we want to talk about Gatorade. Whenever we say electrolytes, students think Gatorade anyway, so I just put it on your take-home test. The electrolytes found in Gatorade, for number 53, are most likely ionic salts and citric acids. Electrolytes are things that conduct electricity. Okay? Strong electrolytes tend to be ionic compounds. Okay? Covalent compounds do not form electrolytes. So in order to conduct electricity, you need charges, positives and negatives, and those are called ions, cations, anions. Okay. So electrolytes are usually anything ionic, and we'll learn later this year they're also acids and bases. Pure water is not an electrolyte because H2O, two nonmetals, is a covalent compound. All right. And then number 56 is also about electrolytes. Circle all of them that would form electrolytes. So we just said anything ionic is, anything covalent is not. So ionic looks good here. Covalent, no way. Okay. Pure water, two nonmetals, no. Okay, let's take a look at NaCl. NaCl has a metal and a nonmetal. That means it's ionic. PO4 are two nonmetals. That means it's covalent. Calcium and nitrogen. Calcium's a metal, so that's ionic. And pure sugar, carbon, hydrogen, oxygen are all nonmetals. So covalent, not an electrolyte. Great. Okay, looking at concentration concepts. We've got another extra credit code coming up. But number 60, you should know this. If you've ever, like maybe you tried to host a club after school and you had 1 gallon of Kool-Aid and a ton of people showed up, so you're like, I'll just add more water. Okay. If you have a gallon of Kool-Aid and you double the volume, what happens to the concentration of your Kool-Aid? Does it taste better or does it taste worse when you add more water to it? It tastes worse. It tastes more like water. So if I am increasing the volume, I decrease the molarity, how strong it tastes, which is an inverse relationship, which is what we were talking about back on page 4. Okay? So if I'm increasing the volume, I am decreasing the molarity or the concentration because I'm watering it down. Okay, there's more water, but I'm not adding more Kool-Aid mix. Okay, and I can even say molarity and volume are inverses or inverse. Okay, so say it like a nerd, like we said on page 2. Okay, inverse. That's the same way we're going to do 61 and 62. Okay, so this looks like it's a math question, and really you could plug it into this equation and solve it if you so feel like it. Otherwise, we're just thinking about it. I have 3 liters of a solution that is a 2 molar. If I evaporate off half the solution, so if instead of having 3 liters, I have half of that, which we'll say half of it is 1.5 liters, okay, what happens to my concentration? So if the volume is going down, my concentration or molarity is going up. Okay, if this is being divided by 2, this one's being multiplied by 2. And then on number 62, I have 3 liters of solution with 2 molar concentration. If I double the volume, so if volume is going up times 2, then molarity is going to go down, divided by 2. Okay? Concentration will be cut in half. Okay, it's that inverse relationship you need to know. All right, extra credit code here at the bottom of page 5. Soda. In the motherland, up in Minnesota, we call it pop. So it's called pop. It hurts my soul every time I call it soda, but you guys don't know what I'm talking about. Humor me. There's your extra credit code for this page. So when I remove the lid on a bottle of soda, you can hear it releasing the pressure. So what happens to pressure when I do that? Pressure is decreasing. I'm letting the pressure out. What happens to the amount of carbonation that's in my soda? Well, the carbonation is leaving, which means there's less of it in my soda. So it's decreasing. Whoops, you know what? I did this one backwards, huh? I said it right, but I did this one backwards. I apologize. When I decrease the pressure, pressure goes down when I open it. Okay? So if I decrease the pressure, I decrease the amount of carbon dioxide in the soda. Okay? Which, if we skip to 66, that's a direct relationship. Okay, they go down together. And then number 65 says, what happens to the solubility of CO2? That's the same question as 64. The amount dissolved, the dissolvability is the solubility. So if pressure goes down, then CO2 is less dissolved. There's less carbonation in my soda. Okay. So that means pressure and solubility of gases are direct. Okay, pressure does nothing to solids, but it definitely affects my gases. Okay. We should be happy when we see this chart. This chart should really help. So what we have is anions across the top and cations here across the side. And for your extra credit code on the page, okay, our fifth one is cations are positive. Okay, cations are positive, right? So when we look down here, the pink ones are for you to do on your own. I want to look at those blue ones together, though. I've got Pb and I2, all right? So lead, Pb in this case, I'm going to circle here, and iodine. So lead is going to come over to here, iodine comes down to here, so that means it is insoluble. Okay. I'll come back and do the name in a second. Copper 2 acetate, right here. So copper 2 and acetate is the first one. So I'd say that is soluble. This will dissolve in water. Sodium sulfates. Okay, sodium right here. Sodium, if you noticed, they are all soluble. Sodium is definitely very, very soluble. All of my sodium compounds here dissolve. But sodium sulfate is this one right here. It's going to dissolve. Okay. I'm going to let you do this part on your own. Make sure you're naming it and doing your 4-step formulas for that as well. Alright, y'all. I hope you found all 10 points of extra credits. Make flashcards to memorize this vocabulary, alright? Good luck.